Right, I said there are 4 things. There are places here later on, but maximal ideals. We had also another notion of defining a point, another way in the formal discussion. I want to formalize that now and relate this. That's going to be easy. That arrow is actually not so easy, but it's also kind of long and tedious. So let's talk about, so this is the picture, we just did it. Now we are going to do the equivalence here. Then I'm going to tell you something about that, and then we're going to do places. That will take like 2 hours or something. So let's talk about the maximal ideal of a ring. The maximal ideal of a evaluation ring. So any questions about where we're going or about the definition of evaluation ring or the relation to valuations? Okay. So here is a claim that will allow us to define the maximal ideal. So now there are no valuations. I'm actually starting with a valuation ring. So let R be a valuation ring with field of fraction F. Then I'm claiming here that M, it should be like a calligraphic M, I don't know how to do it, which is defined by, you take the ring and you remove from it all the units. I'm claiming that this is the unique maximal ideal of R. Start with a ring, and we'll free the function F, but don't worry about that. And what I'm doing is I'm just removing all the units, which is kind of a prerequisite to be an ideal, because if you have a unit, then you generate the entire ring, right? So I'm just removing all the obvious obstacles from this thing being the entire ring as an ideal. Okay? And what I'm claiming is that this is the unique maximal ideal of R. In particular, a valuation ring has a unique maximal ideal. Every ring has a maximal ideal, like by Zorn's lemma or something, but I'm claiming this is the unique maximal ideal. If you know commutative algebra, you know that this means that something is very local here. Like for example, in Z, you have like 2 and 3, every prime gives you like a maximal ideal. Prime ideal, but it's also maximal. And here there's only one maximal ideal. So there are no different like primes or irreducible polynomials. There is only like one. And that really comes from the fact that we are thinking about a unique point. Like 5 for me is also a point. So this kind of hides the 5. So the fact that there is a unique maximal ideal means that I'm local. I'm looking at a point in a sense. But if you don't know commutative algebra, then it doesn't make any sense what I just said. So that's fine also. Less fine, but fine, like for us. But anyhow, let's just prove this thing, right? So kind of by definitions, but let's prove it. And here actually it is interesting that in one order it's easier to prove than in another. And it's the other order that you would think first. Okay, so let's see. So first of all, I'm claiming that there is no ideal that's larger than that, right? Because if there is an ideal that contains this strictly, it contains a unit, and then it's everything. And for me, I mean, it's a technically an ideal, but it's not a maximal ideal. Ideals are, the ring is, I guess, an ideal, but it's not a maximal ideal because by definition, maximal ideals should not be all the ring, the entire ring, if you remember. So once I prove this is an ideal, I'm done. It's going to be maximal because nothing is going to be larger, and it's going to be unique because there is no other way of like reducing one element and adding another element because we get a unit. You just can't add anything that this doesn't have. So it is enough to prove that M is an ideal. Usually it's not. Like with a not evaluation, like usually it's not. Or general rings. So we need to prove it's an ideal, and to prove ideal, you need to prove that it's closed under addition, and that if you take an element from the ideal and an element from the ring, and you take the product, then you go back to the ideal. And we are going to do the second one first. It's actually a good weird thing, but I'm just first of all going to prove that if you take A in M and R in R, then that's what you're going to show. I'm not showing, I'm saying that's true. We're going to show that AR or RA is also in M. That's one thing you need to prove. So let's prove this, but usually it comes after the closed tradition. Okay. So in order to prove that, let's assume by contradiction that this is not the case. So I'm taking A in M, an element in the ideal, and a general element in the ring, and I take the product, let's assume it's not in M. Yes. Because it's so large. Like, once it's an ideal, no other ideal can be larger, contain it. That will show that that's a maximal ideal, because any ideal that strictly contains this contains a unit. And once it contains a unit, you contain. Right. Because I'm shooting for something so big. Like, I'm showing this idea, well, it ought to be maximal. There's nothing bigger than it that can ever be an ideal. But you need to prove it's an ideal. It's harder to prove that it's an ideal when it's large. Well, I don't know. You know, you have more things to worry about, but it's easier to get into. So I don't know about that. But you know, it's harder, I guess. I don't know. I don't know. That's not true. So let's assume by contradiction that that's not the case. Assume by contradiction that, you know, with this A and with this R, RA is not in M. So where is it? It's a unit, right? Because M is everything but the units. So RA is a unit. So this means that, right, RA inverse is in the ring. It's a unit, so in the ring. So RA inverse, this thing is in the ring. Right? And, well, R is also in the ring. I mean, from this, this follows like that, but R is also in the ring. But what is this thing? A inverse. And we just said it's in the ring. But it's not in the ring. A inverse cannot be in the ring because A is in M. Right? A is everything that's not a unit. And we just proved that A is a unit of the ring. This is in contradiction to A being in M, which is exactly R minus, because now A inverse is in the ring, so A is invertible. So A sits here. Yeah. So you right, that's what I'm that's good. That's exactly what I'm thinking of. Where did we use the property of the valuation ring? In the where? Right, that's where I'm going to use it, yeah. But we didn't here. As you said that, I was looking, well, that's just true for general. Good, yes. Well, that's not fair, right? If the ideal is so big, then if it's not an ideal, maybe, but if it's so big, maybe it can have like the swallow property without the additive. Good, yeah, good idea. But let's show, yeah, here we're using. So let's show that it's closed under addition using this. And then we are done. So what you need to show, right, is you give me A and B in M, and I want to show that A plus B is also in M. That's the thing that we're left to show. And we can assume like none of them is zero, right? Because if one of them is zero, then that's obvious. If both of them are zero, it's obvious. So let's just assume that they are non-zero. Okay, now, since R is a valuation ring, either A over B or B over A is in R. Right? That's a trick, but and maybe you didn't expect seeing this, but you know, right? None of them is zero, so I can do this thing. And since it's a valuation ring, it means that every element in the fraction field, which is denoted here as F, either it or its inverse is in R. So let's assume without loss of generality that this one it's going to be the same thing. So let's assume that A over B is in R. So also 1 over A plus B is in R, right? Because 1 is in R. And if I'm going to multiply it by B, because of the small line property, I'm going to be where? I mean, this is an M, right? We proved that M, right? Because we proved that we have the small line property, M times R is in M. But this is what? Okay. So A plus B is indeed in M. Little tricky. The other way around is like harder. That's why I was referring to sometimes the order is important. Okay, so we just moved from a valuation ring, regardless of it coming from a valuation. Just by the axiomatic definition of it, we just show how you can get a maximal ideal. Right, and maybe we can kind of do it here. So M is R minus R inverse. So that's this direction. And now I want to show you that direction. Just, I leave it as an exercise to prove it, but the interesting thing is to think about it, the right definition. So I'm going to do it, but someone gives you a maximal ideal, and he tells you what's the big field F, and he asks you, can you give me the valuation ring that this is maximal ideal? Right, maybe I'm starting from here, I'm doing that, and I'm erasing R, but I'm leaving F. Can you get back R from M? So let me do it more slowly, but that's what we're going to do now. And if you think of functions, as I kind of always suggest you should do, then it's much easier to do. Like, it's not obvious, but it's easier to write down what should be true, and then you can prove it. So here's the game. Right. Say R is a valuation ring with fraction field F, and M is R minus its units, as I said. Now, I want you to write R in terms of M and F, right? And it relates to what you said before. So, right, just let's think about it for a second. If I want, so M give me like a query access, an Oracle access to, given, like it tells you which functions are 0 at the point. That's what it does. And what you want to understand is to kind of reduce or transform this Oracle to an Oracle that tells you which functions are defined on the point, not are 0 on the point. But when a function is not defined point, in terms of when it is some other function, maybe 0 on the point, the inverse, exactly. So the functions that are defined, we should exclude 0 here. Don't worry about 0. 0 is always kind of the functions that are defined on the point, which is not written here, are exactly those functions from all functions for which the inverse is not 0. Right. That's exactly true. You should exclude 0 because 0 is the only function with like infinitely many zeros and stuff. It's always we're going to keep hunting us like that, but mess out the theorems. But that's, I mean, if you kind of look at the dry definition, it's maybe a bit harder to think about it. But if you understand what's going on in the back of the scene, then that's what should be true, right? A function is defined exactly when its inverse is not 0, because when you can invert that, then it will be defined. So that's an exercise, okay? It's an easy one. It's actually a good one to do, but it's also an easy one. So we did now, what we just did is this thing. So moving from a maximal ideal to R, for A such that A inverse is not in M. Okay. Now, before we go out to the break, maybe, yeah. Maybe we'll do it after the break. I don't want to do this arrow, but I just want to tell you what I'm not doing, and it's in the notes. And it's also interesting. It's actually more interesting than this, but this takes like maybe like half an hour to do, and it's not doesn't worth the time. So this thing I'm just going to hint about afterwards, but we're not going to do it, and we're going to move to places, talk about places. Again, it's in the notes. So let's take a break and. Okay, so let's continue. Actually, during the break, someone asked a question, and I think it's a good time to draw a little picture, which is insightful a little bit. I think it should be later in the notes, but maybe. So here's the thing. This is your field, right? And within the field, like maybe kx or something, the rational function field, when you have like, once you think of a point, you have a valuation ring. So maybe, you know, these are all functions with no x in the denominator or something, like defined at 0. And within that, you have its maximal ideal. And in terms of valuation, like these are all the functions. These are the functions that are defined at the point. Like for different points, you'll have different O's. But these are the functions that are defined at the point that you're looking at. And these are the functions that are 0 at the point. So in terms of valuations, the valuation here will be negative. Here it will be positive, and here it will be 0. Right? Because the valuation tells you plus, minus, or 0. Like plus, I mean, like according to the order, larger or equal than 0. That's what I mean. But you think of z, and that's it. So the positive like numbers or group elements tells you the fact that this is positive coincides with, right? The functions here have at least 1 0 at the point. And the functions here in this like ring, not ring like ring, like it's also a ring, but I mean like that part is non-negative and non-positive. These are exactly the units within the ring. And here you have the negatives. So if you have a function here, then its inverse is going to be here. Like a function here, its inverse is here, because and vice versa. Because if you are 0 at the point, then your inverse is defined at the point. And the function here, if you have a function here, where is its inverse? Also here, like maybe it's this one. It's something here. Like x plus 6 is defined at 0, and it's not 0. And 1 over x plus 6 is some other function here. It's defined at 0, it's not 0. And for different points, you have different O's and M's. And also within this M, actually you have M squared and M cubed, like the multiplicity of the 0, but we'll talk about it. Right, so that's a good picture to have in mind. Okay, so I just want to say what I'm not doing. I'm not doing this one, but let me just tell you what the theorem is, and then not prove it. Last time I did prove it, so if you really want to see it, then you can, and you know Hebrew, you can see it. Everyone here knows Hebrew. From the videos from last semester, like 3 years ago or something. And also it's in the notes in English. So, but it's not very, very insightful. So this is the theorem that we are not proving. The reason I'm doing less is because I'm doing it on the board. Last time I did it on slides, and it was very, very fast, and therefore I managed to do a lot. So let F be a field. The map that sends a valuation, the map that we talked about, this one, that sends a valuation to a valuation ring. Induces a one-to-one map between congruence class of valuations on F and valuation rings with fraction field F. A lot of words, but what I really mean is we said almost everything. I'm just saying that this map is actually really a map, as we said, from congruence classes. And it's kind of obvious that it's injective. So like by definition, so valuations that are equivalent give you the same ring. But by the same reason, valuations that are not equivalent, that was an if and only if, will not give you the same ring. So this thing is injective. So like for different congruence classes, you won't get the same ring. That was claim 4 or something. The interesting part is that this error. I'm saying here that this is a one-to-one map. So namely, you can invert. So given a valuation ring, which you don't know what the valuation or congruence class of valuation that led to it, if you start from every valuation ring, you can get it back up to an equivalence. And it's not so easy. And the reason, the hint that it's not so easy to do is because if you think about it for a second, you're given a ring, like think of the types, you're given a ring R with field of functions F. F is always there. F is known from the get-going. Otherwise, you can just take a bigger F. But so you're given a valuation ring, or just a valuation ring in F, like with fractions in F. And somehow you need to produce a valuation which takes an element from F. So at least this thing I know how to write. But then I should produce something in what? Ordered group. Where are you going to come with an ordered group out of the valuation ring? Like it's a different type. I'm giving you, technically this, I'm giving you a ring, and you should find a group which is usually sometimes Z, but sometimes not Z. It's not clear how, like just the types, how you can even do that. And actually, all the little lemmas that we had, like 1 or 2 lemmas that we had about ordered groups and their relation to submonoids and so forth. So really, what you need to find is a submonoid, not an ordered group, and for some group, and that's kind of easier to do, but it's not so easy. So it's like 20, 30 minutes on the board, maybe more. So I'm not going to do it. What I am going to do is an example. I continue with the usual example. Yes. So I'm trying to keep this picture, and just let's do an example. You have the ongoing example that we are going to keep like developing, and check against the things that we are like defining. So I don't know if you remember. So let me just remind you. We looked at the field FQ, and within that field we look at fxy, which is y squared minus xq plus x. Right? And the two things we did was to kind of like just play around with it, but we just defined what's called sometimes the coordinate ring. So you should think of it as all polynomial functions. We had all discussions about it. Polynomial functions defined over the curve, but I'm not saying really what a curve is and so forth, but And then we saw that because this is irreducible, this is a domain, and so there is a fraction field. But we actually gave an explicit description. We just said that, no, sorry, we had that. And then I told you that I'm thinking informally. That's what I'm thinking. Like I'm wondering, thinking about the point 0, 0. Like this is a point in the usual sense, like coordinates. Like you have 0, 0, 0. So I'm thinking of this this thing on the curve, which we called ZF, I think, last time. Just the curve, the set of all solutions to these equations. And there I told you that there is a valuation that corresponds to that point. That's actually 0, 0, but I'm just writing a 0 here. And that valuation, we said exactly how it looks like. It looks like this. All right, so we did say that every element in the fraction field looks like that. For you have rational function in x plus a rational function x times y, because y squared can always be kind of removed, and we did this kind of trick by multiplying by the conjugate and so forth. So every element in KF looks like that. And then we said that this is exactly the minimum between like a simpler question, the valuation of the individual like rational functions. And here the y gives you a 1 because we proved the valuation here is 1. And we use the strict triangle inequality with this little trick that this is even and this is odd and so forth, right? So we proved this thing last time. where ax and bx, I'm doing it fast because it's just a reminder. And now let's try to figure out what's OA, what's O of that valuation, and what's M of that valuation. Okay, that's what I'm trying to do now. Just as an exercise. And it's kind of a weird exercise because we never really proved that's a valuation. And I kind of use the fact that V0 of x is 2, but given that, let's do that nonetheless. So what is O of 0? So technically, just by definition, these are all the functions in the function field. Usually you have k round brackets x, like rational functions. But here it's like more interesting. It's fractions like that, which in this particular example looks like this: rational function in x plus rational function in x times y. Like you never need 1 over y, and you never need higher powers of y, because we did a conjugate trick. All of these for which you get a non-negative evaluation, like here. And in our case, so you will help me, but let me just write it down in the language so that you can say what's true. So any element z in kf, we said, looks like this with rational functions, but let's break it down to polynomial division, like that, where these are co-prime and these are co-prime. And what do you think you should hold, for this to be non-negative, in order to get that this thing is non-negative? Like, what should you expect from A, B, C, and D? Right. Each one of them should be greater. Exactly. So, right? And let me just skip one step, because in this particular example, we can write it like that. Right, I'm assuming A and B are co-prime, and C and D are co-prime. And because of that, you can clean exactly what Itai said. You want the valuation of this to be non-negative. I mean, the minimum should be non-negative. So this should be non-negative, and this should be non-negative. But this is like multiples of 2. So for this to be non-negative, technically this could be -1. That's also okay. But it's a multiple of 2. We proved last time. So actually, you need this to be non-negative and this to be non-negative. Because once this is negative, it's a -2, which is bad. And technically, I wouldn't mind a 0 here and a -1 here, but that doesn't. The granularity here is in 2s. So I need this to be larger or equal than 0 than that. In terms of the polynomials, after you write the polynomials and you use the coprimeness, it means that B of 0 is non-zero, because A of 0 you can't both of them be 0, because it's coprime. So B of 0 should non-be 0, and D0 should non-zero, and of course A and B are coprime, and C and D are coprime. I'm kind of taking the more general definition and choosing representatives, and in that language it's kind of elementary to say, like in terms of without valuation. It's just B0 is non-zero, D0 is. So any function that you can take here, you can write like that. You can clean common factors here, and then the answer to the question, what are the defined functions, are these. And it's actually interesting because I don't know, like maybe y has a pole, but x is kind of stronger. I don't know. Never mind. Don't worry about that. And what is M0? So technically. Right. So the valuation of a rational of this thing is the valuation of this minus the valuation of that. And we want the valuation of this to be non-negative. So it's enough that the valuation of this to be larger or equal than the valuation of that. But because I'm assuming coprimenesses here, I'm kind of choosing a representative, which valuation don't care about. But for us as humans, it's easier to kind of write constraints in terms of the polynomials, not just like a valuation of something. Then this is exactly the case in which the B0 is 0 is exactly the case in which the valuation of this is larger than the valuation of that, because this has a 0 and this doesn't have a 0. If it's 0, it will put me in M, and if it's not 0, and then if it's not 0, it will be a unit in that sense. And what is M0? again, it's not a completely formal because it's formal given what I told you. But so when are from those functions, which are those that are 0 at the point? So you may want to say that both a of 0 and c of 0 should be 0, but actually you don't need the c of 0, only a, exactly. So what I'm claiming, so how do you see it, Itai? By definition of something? Exactly. So these are all. Yeah, it is going to be like this, and as well as another constraint. So this thing is, I mean, I want this to still be satisfied. So this is going to be part of the ring. But the extra information I need is that a of 0 is 0. That's what I'm claiming. So it's part of the ring, right? It has more constraints than to be in the ring. But why is this true? Let's just before do the sanity check. Why is this true? So to be here, you need to be here, but you also need this to be with strict inequality to 0. So you need the minimum to be strictly larger than 0, right? So you need this to be strictly larger than 0 and this to be strictly larger than 0, because otherwise you're at the minimum. So you need both of them to be strictly larger than 0. This strictly larger than 0 is really just saying that, including the b0 is non-zero, but saying that. And to say that this is strictly larger than 0, you don't have to say anything, because it's 1 plus something even, and it is enough to require that this thing is larger or equal than 0, which we already did, in order to require that this is strictly larger than 0. So you see, the valuation kind of tells you something which might have been harder to guess. In this case, it's actually easy to guess, because this should be something about evaluating at 0. And when you evaluate at 0, y is 0, because the point 0, 0. So you don't really have to worry about this. You plug in y equals 0 anyhow. So you really just need to make sure that a0 is 0. That's the intuition, but that's the formal thing. That's how.